Welcome to the MIT Center for Art, Science, and Technology's 2021 Symposium, Unfolding Intelligence, the Art and Science of Contemporary Computation. CAST was established in 2012 with the goal of building and building on connections between the worlds of art, science, and technology. This is the third in a series of symposia that CAST has convened since then, and as with its predecessors, we bring together artists, scientists, engineers, and humanists from within MIT and from the world at large to discuss areas of rapidly evolving research and urgent social relevance, and to find in that dialogue stimulation, confirmation, provocation, intersection, and, we hope, common purpose. At MIT, CAST partners with departments, labs, and centers to integrate the arts across the curriculum, to enrich and encourage artistic collaboration, and to provide support to faculty and members of the MIT community as they pursue their own artistic practice and/or research. In addition to symposia like this, CAST facilitates the sharing of this creative work beyond the Institute by producing concerts, exhibitions, and publications, and making them available to the public. So, thank you for being with us today. We hope you will join us throughout the week at virtual events addressing the aesthetic, technical, and critical issues pertaining to artificial intelligence and computational media. We also look forward to seeing you on Friday, April 9th, as the symposium culminates with a live interactive event to which all attendees are invited and in which you can join presenters and artists in breakout rooms to explore hidden threads between all that has been discussed this week.
Welcome to the Unfolding Models panel of the Unfolding Intelligence Symposium, convened by the MIT Center for Art, Science, and Technology. I'm Professor of Anthropology, Stefan Helmreich, and I'm thrilled to introduce to you three exceptional speakers for this session. Yale University physicist and Professor of Astronomy, Priyamvada Natarajan, Yale University Professor in Ecology and Evolutionary Biology, C. Brandon Ogbunu, and glitch artist and resolution theorist Rosa Menkman. In this session, we examine how tools and computation shape the models that scientists and artists make of the universe, the world, and of models themselves. Dr. Natarajan, a leading investigator into the character of dark matter in the cosmos, will show us how computer simulations of intergalactic clustering may disclose dynamics otherwise impossible to see. Dr. Obunu, working at the intersection of evolutionary biology and epidemiology, will discuss how mathematical models of such phenomena as the COVID-19 pandemic may be leveraged to help us decode the causes and consequences of disease across scales, from the biophysics of proteins involved in drug resistance to the effects of structural racism on health chances and outcomes. Rosa Menkman, a visionary in the field of glitch art, asks how the materiality, structure, and resolution of data formats contour scientists and wider public's sense of what computer simulation can show and mean. Questions that she asks by zeroing in on and curating moments of noise and stutter within the circuits of both analog and digital representation. As you watch the presentations of these extraordinary thinkers, I invite you to think across them about how computer models can act as theory animated in cosmology, biology, aesthetics, with consequences that may be all at once epistemological, political, and world-bending. Think of the models that unfold through computation as abstractions made code, made new tools for representing and intervening. I'll close and open with an acknowledgement that MIT sits on the traditional unceded territory of the people of the Wampanoag Nation, traditional stewards of this land, who have endured a painful history of genocide and forced occupation, and who, along with other indigenous peoples, as well as those who have suffered under conditions of unfree labor, are still here, working to survive and thrive. Now, offering an acknowledgement like this through the many reticulated loops of data, clouds, and cables it requires brings our bits to you through a tangle, a glitchwork even, of further land, air, and sea sovereignties, something that requires us to think afresh about what we model when we model with computers, about how computation enabling acknowledgement based protocols like those of the Transmission Control Protocol, or TCP, might be remodeled to serve better and more just unfoldings of our knowledge and politics. Please join me then in thinking through questions of what kinds of universes and worlds might yet be made in silico and beyond.
Hi, I'm Priyanatarajan, an astrophysicist and cosmologist at Yale, where I'm also the director of the Franke program in Science and the Humanities. A lot of my work involves the analysis and running of cosmological simulations. And I am delighted to be invited to speak at this very unique and exciting conference on the art and science of contemporary computation. So I would like to thank the organizers for this opportunity. And I'm going to argue and hopefully persuade you at the end of my talk that simulations in cosmology play a very, very special role. They play a mediatory role between theory and observations. Astronomy, as you know, is an inherently observational science, and it is the power of the image, the visual, that has a key role in driving discovery, explanation, and creation of new knowledge. That is quite apart from other fields in physics. And cosmology, in particular, cosmological simulations, are also distinctly apart from their counterparts in other subfields in physics and other sciences where computation has come to play a significant role, because they will, as I demonstrate in the talk, they actually play a generative role increasingly, especially with the combined use of machine learning techniques. So the old critiques of the role of simulations posit that computer simulations do not really yield any new knowledge or understanding about the world because we put into them what is already part of some pre-existing scientific model. Since we create the model, we must know it very well, and at best, the computer simulation might make the consequences of the model visible. That is, it shows us the solutions within the space of possible solutions for the model and allows us to see how the simulation, given some boundary and initial conditions, will play out for us full nonlinear exposition of the underlying model. Moreover, there are no guarantees that the computer simulation, just as any other physical mechanism, would be error-free. Indeed, computer simulations have limits in terms of their resolution and their reliability, but our input assumptions do ratchet into and impact our conclusions, as one of the case studies that I will talk about today will show. However, as I hope to show you today, there are enormous epistemic gains due to this unique mediatory role that cosmological simulations play. Simulations are not just a direct implementation of a scientific model on a machine, they vastly enhance our creative capacity, expand what can and is explained, and open up new windows and realms and facets of models that are not amenable to pencil and paper calculations. Just as physical theories are certified by experience and expertise, at least this is what we've believed so far, while analyzing other subfields in physics, simulations play a very important epistemic role in cosmology due to some of the inherent paradoxes in cosmology. The simulations offer a very novel and powerful way of reasoning and exploring properties of theories and models of a single universe that we have, one that we are sitting in the middle of as we observe and cannot perform controlled experiments. I think the key thing that distinguishes cosmological simulations is the fact that in cosmology, we cannot perform controlled laboratory experiments, and that simulations are the proxy that permit us to do that. Philosophers of science like Peter Gallison have argued in his wonderful book, Image and Logic. He's examined the practice of science in particle physics, has interrogated the diversity of scientific subcultures that participate and collaborate in the production of data. And he proposes this idea of a trading zone, trading between theory and experiment, an uneasy yet immensely productive exchange in relationship between these communities that ultimately is what he argues brings strength and stability to the created knowledge. To understand the role of simulations in cosmology, I am going to argue that we need to go beyond the idea of a trading zone. And in fact, we need to see them, simulations, as a new kind of language, as an interglot. This is borrowing a term from linguistics, where the concept of a universal glot, we have this concept where it's a new language that comprises words and concepts borrowed from multiple other languages that aims to be intelligible to all. So in linguistics, an example of this would be Esperanto. So I am going to argue that cosmological simulations are actually an interglot. They shape, permit reconceptualization, redefining the landscape of discoveries in cosmology. So observations, theory, and simulations together play a very cohesive, dynamical, collaborative role in creating new knowledge. And simulators are increasing a highly professionalized, respected cadre within cosmology. And in our data-driven, computational, advance-driven science and technology research terrain, simulations have started to play a much more significant role in the production of new knowledge. So here's the outline of my talk today, where I'm going to talk about what is special about cosmology and numerical simulations of the universe, what specific purpose they serve, these simulations, and how the simulations are different from laboratory experiments. And in particular, I will focus on two case studies that focus on the black hole growth problem, which is trying to understand how supermassive black holes grow in the context of structure formation in the universe, the formation, the fueling, and feedback of black holes. And in particular, I will focus on some correlations, observed correlations, whose deeper underlying causation we are yet to really comprehend. First, I want to discuss the paradox of cosmology. So the paradox of cosmology is that there's some fundamental, insurmountable epistemic limits. That is the fact that the inability to perform controlled experiments on the universe. So we have one universe, and we have a peculiar vantage point that we are inside this universe, we are making observations, and we are trying to construct an understanding of this universe. And additionally, from what we know so far, the dominant constituents of this universe are invisible, and their presence is inferred only indirectly. There are some surmountable limits, and they, of course, have to do with the limits of models and tools and ways of knowing. And structure formation in the universe is modulated by unseen entities. So the primary constituents of the universe are dark matter, and dark energy. So dark matter influences the universe by gravity, and it offers the scaffolding within which all the other assembly of structure happens in the universe. Dark energy, we believe, drives the accelerating expansion of the universe. And black holes, that we now know, seem to play a much more significant role. Once believed to be quite marginal, they play a very significant role in modulating the formation of galaxies. Simulations, as I mentioned, act as very important mediators. So they serve as epistemic arbitrators, and they serve as this interglot, this sort of language, this new language that has common elements with both observations and theories and models, and permits communication, seamless communication, feedback from these two realms. And I will show you with these two case studies that simulations serve to provide explanation, evidence, prediction, exploration, as well as confirmation. And particularly with the augmentation of simulations with machine learning techniques in the creation of new knowledge, we have some really interesting new explication of what simulations can do and what kinds of new discoveries they might be able to enable. So, the two case studies that I will be looking at that highlight the predictive power of simulations. So, the first is a simulation to study the formation and growth of black holes and their host galaxies. And here, what I want to illustrate is the implications and impact of input assumptions on the output. So these are simulations of structure formation where, as I said, in the scaffolding of dark matter that aggregates only via gravity, normal matter falls in, you form stars, and you form a black hole that sinks to the center of galaxies and grows over time. So the input assumption till now, till very recently, except for this one new simulation that we have performed and analyzed called Romulus, is that these supermassive black holes were pinned to the centers of the galaxies where they form and grow. And so they were artificially pinned. So the consequence of part of the initial conditions, now the consequence of relaxing this assumption, what is revealed in the simulation is an entire new population of wandering supermassive black holes. So I want to illustrate that with the simulation and show you the impact of relaxing one assumption. So this is addressing the issue of how the input assumptions shape the output of a simulation. And in many cases where restrictions of the input actually circumscribe the kinds of new discoveries and new knowledge that you can get. So in this case, we're actually generating new knowledge, uncovering an entirely new population of black holes. And the second case study, I'm going to show you a brand new project in which we have created a new platform which co-locates observational data and simulations that enables new kinds of machine learning techniques to be used to disentangle this deeper causation and correlation that I mentioned previously. So what you are seeing here is sort of the basis of most underlying cosmological simulations. And I have separated out in two panels for you the underlying dark matter, which is the web, which is the cocoon in which all the other activity that you are going to see on the right-hand side, which is the formation of stars, the gas that is falling in, the growth of the black hole, and material that's falling into the black hole is generating these hot bubbles of gas that you're seeing colored as red on the right-hand panel. So in effect, the simulation that I'm going to show you actually does all of this at the same time. I have separated out these two views to show you roughly the sort of the relationship between these various components of the universe. And as I mentioned, the driving kind of question for all of us in cosmology is the causation, sort of this connection between the black hole, the host galaxy that it's sitting in, and the larger dark matter halo, the parent halo that hosts all the activity. So let's move to looking at this particular simulation, and I'm focusing now on one little portion where we are forming a spiral galaxy. This is a part of the same Romulus simulation that I just showed you. And this is the impact of relaxing the assumption of pinning down black holes artificially to the center of their galaxies, holding them down. If you remove that anchor, and you can see these little white dots around the spiral galaxy, these are the wandering black holes that have been brought in as the galaxy is assembling during mergers that we saw visually previously. And on the sides, I show you these thumbnails of these recovered populations of wandering black holes. So this is an undetected, as yet undetected population of black holes that is predicted. And now these simulations have predicted the existence of this population and have allowed us to understand the properties of this population, the demographics and the properties and the origin. And so now we can devise strategies, which we have done in a set of papers, to go look for them. So this is a remarkably different role that simulations have started to play. And, and it's come out of relaxing one limitation of the simulations. So here I'm sort of going back to showing you the integrated elements again, this movie of the Romulus simulation, where you are simultaneously seeing the dark matter is not visualized here, and what you are seeing is the baryonic or ordinary matter, ordinary atoms, and you see gas flows, and you see stars forming and galaxies forming at the intersections of these nodes of these filaments, and you're seeing these gas bubbles that are blown. So the activity, the flows, the activity in terms of star formation, and feedback from energy feedback from the material that's falling into the black hole that is heating up the gas, is all simultaneously seen. So we are now able to visualize this underlying black hole host galaxy parent halo connection. But what we really want to do is to study it more deeply. And the challenge with that has to do with the fact that we have a lot of empirical data. So here are a few correlations that are seen in nearby galaxies that all contain dormant supermassive black holes. So these are not black holes that are blowing the bubbles like the ones we saw in the simulation, but these are black holes that are sitting. They have grown to the largest possible size they can, and they've reached a maximum size. They are sitting and they are not actively growing anymore. So what we see, and that is the case with all the black holes seen in nearby galaxies. And what we find is there are very interesting, strong correlations between the properties of the black hole, that is the mass of the black hole, and the mass of the host galaxy, the luminosity of the stars in the inner region of that host galaxy, and the velocity dispersion of stars in that host galaxy. So the question is, these are important correlations between properties of the black hole and properties of the stars that are hosting the black hole in the galaxy that's hosting the black hole. This is the central black hole now. We're not talking about wanderers. I've moved on to the second case study. And so the question that we've all been grappling with for decades is, do these correlations actually point to some deeper physical causation? Is this a causation that is set up? Do these correlations reflect some causation that is set up in the very early universe? And the growth, the simultaneous growth in tandem, do they reflect a growth in tandem of the stellar component and the black hole? That kind of makes sense because they both grow from gas. However, we don't know if this is a property of the initial conditions of how black holes form, which we don't quite understand yet. We have some ideas, we have some theories that stand to be tested and validated still with more data. But this question is really an open one, and it's the most important one in understanding the growth over cosmic time of galaxies and their black holes in the framework of these dark matter halos that both entities actually sit in. So the question, as I said, how the first black holes form, we don't know. How they actually grow, we have some clues. And how they couple those bubbles that we saw is something that we do understand. But what is interesting is that although we have data that now reveals to us populations of quasars, these growing black holes, out into very early epochs in the universe, that data is highly incomplete. We only detect the brightest objects at earliest epochs because of the distance of how far they are from us. And so we have an incomplete sampling. So the quantity that we would really like to derive from observational data that would inform our theoretical understanding models, and that we would like to recover from simulations simultaneously, ab initio, are two quantities. The black hole mass function, which is the derived distribution of black hole masses as a function of cosmic epoch, and the luminosity function of quasars as a function of cosmic epoch. So these are two constraints for our models, and our simulations need to reproduce these constraints. So in order to do that, to deal with the fact that simulations have limited volumes, even with the advances in computing, we cannot yet simulate a volume of the universe that corresponds to the size of the observed universe that we are actually probing with our telescopes at the moment. So there's a real mismatch. So in the data, we have incomplete data because we preferentially see only the brightest quasars. And with the simulations, we don't have an adequate volume to reproduce and mimic the volume of the observational survey in which we are detecting these quasars. So, in order to bring them both into synergy, we just recently started a long term project, a very exciting project that I'm leading at Yale, which is called QuasarNet. And it's a new research platform that leverages machine learning techniques for the data driven discovery of black hole populations, hitherto undetected black hole populations. And so, what we've done is we have co located observational data and dark matter halo data from simulations. And the idea is that we want to perform association studies. We want to associate observed quasars with locations in these simulations. And of course, we have to use machine learning to enhance the volume of these simulations to match the corresponding survey sizes in which these quasars are found. And then we can make a whole host of assumptions about how to associate quasars with particular locations. And then we can use machine learning to derive the properties of as yet undetected. And why is this important? This is important because we expect a real deluge in observational data in the coming decades. And so let me briefly tell you, give you some features of the power of simulations, and in particular, the way they are leveraged in QuasarNet. And it has to do, of course, with visualization and the discovery of new correlations. So these are just a few outputs from QuasarNet. So all of our data and codes is available online on the Google public Kaggle platform. So these are just some visualizations from QuasarNet of the data. So we've compiled observational data of high redshift quasars. All known high redshift quasars detected optically are part of QuasarNet. We've homogenized it. It was very painstaking work. And what we can then do with this collated data is we can look for all kinds of correlations. And that's what is shown in the central panel. And we are able to construct this black hole mass function that I mentioned is one of the key inputs that informs our models and the simulations. And so the other thing that we can do, I talked about the association, and what is shown here is what is called a halo merger tree, which is tracking the assembly history of dark matter shown in the black dots over time, and the galaxies that form in these halos and the black holes. So what is shown in red is the most massive dark matter halo at any given time, and as a function of epoch. So you see the buildup of this dark matter halo that you see at the end is the most massive one. And this most massive one most likely hosts the brightest quasar. So we can play these associations. We can locate the brightest quasar in the most massive halo, and then we can trace back the assembly history of that black hole in tandem with the assembly history of the parent dark matter halo and the host galaxy. So these kinds of new studies are going to become possible now. And as I mentioned, the current key limitation for doing this kind of correspondence, direct correspondence between observational survey volumes and simulation volumes, is sort of the mismatch at the moment. But with machine learning, we can start with a small simulation box with very high resolution, and we can use machine learning to derive the characteristic properties, learn and derive the characteristic underlying properties of all the dark matter halos and galaxies in that simulation, which will then allow us to draw from that distribution to enhance the volume, to create a much larger volume simulation, one that is matched to the observational data better. And then we can do these association studies to ferret out the causation for some of the correlations that we actually see. So this is sort of new work that we're doing that I'm very, very excited about. And it really illustrates the power that cosmological simulations have. And in terms of generating discoveries, they were never believed to be generative. But I think we are now seeing that in combination with machine learning in particular, it is starkly seen that they could be driving discoveries in the next couple of decades. So I want to close with thanking my collaborators and give a shout out in particular to Sunny Tang, who is a graduate student at UIUC, who did a lot of the heavy lifting for QuasarNet, and my former PhD student, Angelo Riccardi, who has done a lot of the work on the black hole growth models, Michael Trevell, a postdoc at Yale, who was part of the team that developed the Romulus simulations that I showed you that we are using for our analysis, and my many other collaborators. I also want to thank Google X for their support with computational resources and collaborators on this project, and a whole host of computational resources across national facilities, locally at Yale, and so on. Thank you very much for your attention.
Greetings, my name is Brandon Obunu, and I'm here to offer some thoughts on the concept of unfolding models in the context of cutting-edge questions in biology. When we think about this question, right, about unfolding, right, one of the curiosities that I think about is what does that actually mean in the context of something like biology? And what I've interpreted as is something about kind of like disentangling, right? Unfolding can mean many things. It can mean kind of just exposing, revealing. But I think biology in particular offers this means of thinking about unfolding in a particular way. Now, what do I mean by disentangling? And what, in the context of biology, are we attempting to disentangle with models, right? I think maybe most famously, most notably is the concept of protein folding, right? And that one is very literal. And I think that one has kind of gotten a lot of press recently, in particular in the computational realm, for the tools that we're using to solve this protein folding problem, right? And the idea here is that biological information, right, is encoded in a certain manner, but really operates in a three-dimensional means. And that kind of is a difficult challenge to understand how you get three-dimensional structure from kind of unidimensional information. But I would offer that, right, the analogy of folding and disentangling goes much further. We can go back to Darwin, one of the most famous passages in all of biology. Darwin talked about how it is interesting to contemplate a tangled bank, right? And what Darwin was talking about in this context is the notion of life interconnected, that the biosphere and that the laws of natural selection are operating on all of these different species in all of these different ways. But this tangled bank analogy is profound, right? And I think importantly in this famous passage, right, he talks about how this tangled bank is the substrate through which these laws have been acting around us, these laws of nature, and of course, evolution by natural selection, right? And so really a lot of modern biology, and really biology since Darwin, and even before Darwin, has been about kind of taking this web, taking this tangled bank and disentangling. And we can kind of move that towards very modern problems, right? Right? So for example, you think about modern ethical issues about genetic modification, ethical issues about genetic determinism, about gene editing, right? Or just kind of even, modern kind of AI and machine learning informed problems writ large. And a lot of it is about kind of this mishmash between the data that we're collecting, the things that we want to understand, and the implications they have for society, right? Now, of course, these are outside the scope of any presentation, but these are all kind of cutting edge modern problems where this tangled bank that Darwin introduced us manifests, right? Right? But much more practically in the context of biological problems, right, disentangling involves better understanding the flow of information through something we call the central dogma, right? The central dogma is itself a type of model. And what it describes is the flow of information from DNA to RNA and protein and all of these other variations. But though the central dogma is a very simplistic description of the way biological information works, right, as you'll see on that figure on the right, the fact of the matter is it is a very, very complicated act to go from biological information, genotype, to phenotype or fitness, as evolutionary biologists would describe it. It is in our effort to disentangle this tangled bank, the one that Darwin described originally and has manifested in a lot of modern problems, that we really need models. Models kind of allow us to make sense of these types of things. We'll describe several kind of conceptions of what models are. We'll start with one that was introduced in philosopher Daniel Dennett's Darwin's dangerous idea. And what Daniel Dennett discussed was the notion of being able to understand kind of the way a calculator works. And when you ask the question of how a calculator works, what are you asking? He was talking about the notion of why is it that when you put a certain computations in, you get a certain answer. And what he said was that understanding a calculator at the level of every individual electron and the way that works at a great level of detail does not really help you think about the way the actual calculations are done, right? And the way he kind of introduced this and brought it home was by describing a calculator that computes wrong answers, this hypothetical thought experiment of a calculator that computed wrong answers. In that situation, if your job was to understand why a calculator was kind of producing wrong answers, understanding these electrons would not help you there. And so it's important to think about what is the thing that we're curious about? Like, what are we trying to model, right? Are we trying to model the way electrons are flowing through a set of circuits or what have you, or the quantum behavior of electrons in this system called a calculator? Or are we trying to get to the computational logic of why it is this instrument is producing this answer? And so the key point here is that it's critical that the anatomy of the model and the understanding embedded within it reflects the level of the question, right? Understanding everything at a really, really, really infinitely reductionist level does not help us answer all of the questions. And this is where kind of a little bit of understanding comes in and domain expertise comes in. The other kind of conceptions of models, right, can be captured by these famous quotes. This one by George P. Box, that all models are wrong, but some are useful. And this other one by Samuel Carlin, that the purpose of models is not to fit the data, but to sharpen the questions. Now, each of these kind of capture, right, various aspects of the way we think about the purpose of models and what they're good for. This first quote by George Box kind of actually captures some of the flavor of Daniel Dennett. And the notion there is that, right, well, you know, we don't need to understand everything about the system. We just need to understand something about it that it kind of addresses a question that we're interested in. And somewhat relatedly, Samuel Carlin is basically saying that, well, it doesn't have to reflect reality, but it has to kind of give us something that allows us to be able to create better questions that we can now take forward, right? And, you know, those are kind of useful quotes in some regard, right? But there are other conceptions that we can think of that are much more detailed, right? How about like the model as a scientific instrument, right? You can think about this, be it a turntable or a woodwind instrument or whatever instrument you want to think about. All of these instruments can play songs, they can cover a remix songs, and they can be used to kind of play new music and offer the world new music, right? Similarly, we can think about it as a scientific instrument. It can recapitulate or explain past phenomena, right? It can understand and predict yet unseen phenomena, or it can generate new questions and hypotheses. So in the context of an epidemic, for example, a lot of mathematical models try to understand the way an epidemic happened. And that's important, right, for us to kind of potentially being able to predict future ones, to understanding how is it that 1918 influenza happened the way that it did. Of course, the understanding and predicting of yet unseen phenomena is really, really important, because this kind of allows us to potentially predict things that haven't happened based on information that we have. Now, this one is obviously contentious in the modern times in the context of the pandemic, because a lot of models, right, haven't been exact and accurate, but they've been important nonetheless. And lastly, sometimes models are just theoretical, and they allow us to kind of highlight what our ignorance is. All of these are important uses of models, right? There are different modeling instruments. We talked about kind of whether it's turntables or woodwind instruments. You could use that analogy. We can use mathematics and computer science, and there are different kind of ways that we can kind of capture different aspects of reality. Mathematics, of course, is very kind of transparent. It puts all of its assumptions out there, and there's still discovery in the process of mathematical modeling, but you see what the pieces are very clearly. Whereas with computer science, right, there's a lot of what we call black boxes. Of course, the strength of computer science approaches, like agent-based modeling, for example, is they allow you almost infinite control over what the agents are. So in the context of an epidemic, you're not assuming that all individuals in a population are the same. These are assumptions you often make in mathematical models. In computational models, you're able to kind of wire individual behaviors and therefore ask a different set of questions. And we can kind of see this playing out, right, in the context of a mathematical model. These are both of cholera outbreaks. All right, and one of them is kind of a mathematical kind of simulation that looks at the way that different intervention strategies influence the dynamics of cholera. In the context of computer science, you can capture a lot of the capriciousness of epidemics with regards to how individuals operate and act over space, place. Right? But the one I want to focus on finally, and where I've put a lot of my recent effort, is this notion of the model as an analogy, right? You can even think about from Punnett Square to the central dogma in biology, these things are all stand-ins for something. Now, they're often quantitative, but not necessarily, right? The central dogma, DNA to RNA and protein, doesn't have any numbers in it, but it is a model, right? An incomplete one, the one that we continue to prove on for the way information works, right? And one very, very famous analogy we'll use comes from John Maynard Smith. This one's been transformative for a lot of people. In 1970, John Maynard Smith published this paper, Natural Selection in the Concept of a Protein Space. And in this manuscript, John Maynard Smith offered an analogy for adaptive evolution in proteins that ended up becoming profoundly influential across a lot of different disciplines. The 2018 Nobel laureate, Dr. Frances Arnold, discussed the importance of this paper in the trajectory of her own work during her Nobel lecture. Now, what did John Maynard Smith do in this manuscript? He basically compared evolution to a popular word game called Word Ladder, right? Right, that many of us have played. And the idea here is the goal here is to go from one word to another, changing one letter at a time. And in this context, right, you could ask the question, which of these is a winning path? That wouldn't the path from word to war to gore to gone to gene would be the winning path because all of the words are meaningful. And the idea here is that an evolution can move through space in an incremental fashion. It does not need to solve complicated problems all at once. It can move through it kind of in an incremental manner. Even more so, John Maynard Smith's analogy is important because it identifies that solutions to adaptive problems are often located in networks. For evolution to work and be a kind of an effective algorithm for solving problems, it need not search the entire expanse of possibility, but it needs to kind of search local spaces in order to find solutions often. So it's a profound analogy, right? It's a rich abstraction, right? And it kind of contains many other ideas within it. This idea of a fitness landscape, adaptive trajectories, all of these kind of complicated problems live within protein space, right? Because you can kind of take this metaphorical protein that John Maynard Smith identified, and we can think about, like, we can ask some questions of it. What if we're thinking about something different? What if we're thinking about an actual protein defined by 4 amino acids, described by those kind of single letter substitutions? And we were asking something about, okay, well, how does an enzyme that is the target of drugs evolve drug resistance? We can ask the same types of questions that John Maynard Smith asked in 1970. So from this gamified analogy, we can recapitulate a lot of the importance of kind of biology and important questions in evolutionary biology, right? And using this abstraction, right, we can get to fundamental laws, and one that I think is as cutting edge and important as any law in science, one that we don't have yet, a fundamental law of evolvability. When John Maynard Smith was describing moving from word to gene, he was describing the ability of evolution to be able to find solutions to complicated problems. I would argue that models like this one can frame the next generation of important ideas in evolutionary biology. The notion that not all things are evolvable, and maybe we can be able to predict the direction that evolution will move. I would argue that this is right up there with the unification of the laws of physics. So in closing, we can talk about what does it mean to unfold models? Unfolding models articulates several important points. The fact that we can use them to disentangle, right, complicated problems defined by multiple actors and operators, like epidemics. And we can use very, very simple models like the kind of word ladder analogy for protein evolution to consider basic questions about evolutionary possibility. This would influence agriculture. This can influence the way we think about predictive evolution in the context of epidemics, genetic modification, biomedicine, all of these problems defined by the uncertainty in being able to predict evolution are the type of questions where models can help us move forward. At this time, I wanted to express my gratitude to all the individuals involved with organizing and creating this important space that is unfolding intelligence. This is a critical time to be asking these questions, and I've greatly enjoyed this opportunity. Thank you.
I would like to thank both Stefan Helmreich and Dana Solomon at Cast MIT for letting me present resolution studies in this special occasion. My name is Rosa Menkman and I'm a Dutch artistic researcher. Last year I released a little book titled Beyond Resolution. And in this little book I probed the field of resolution studies through the computational image, both practically and theoretically. In this presentation I would like to highlight 3 main perspectives from this research. First, an ecology of compression complexities. Second, the rheology of data. And finally, the impossible image and its latent image space. But I'll start with a short introduction into what actually is resolution studies. A technological resolution is the result of a consolidation, or the bridging, of the material qualities of certain objects. They involve, for instance, shutter speed versus aperture, the type of CCD chip, or other standards, such as interfaces, protocols, etc. In short, the setting of a resolution comprises of the designed affordances of these objects. And as a result, and I think this has already been well described by Alex Galloway in his book The Interface Effect, they influence the final use of the technology. The standardization of resolutions is a process that generally imposes and enforces efficiency on our technologies. But it doesn't just involve the creation of protocols and solutions. It also entails the obfuscation of compromises, and by doing so, resolutions black box alternative possibilities, which are as a result in danger of staying forever unseen or even forgotten. For instance, in terms of data, 0 and 1s, on and offs, raw data or even JPEG encoded data, formatting defines not just how it's stored, shown or sent to and between technologies, but also what data is actually stored. Because while some data is privileged or preferenced, other forms of data are unsupported and even cut away. So the cost of media resolutions are that we have gradually become unaware not just of the habitual choices but also of the compromises they represent. And as such, the habituated violence they inhibit. A dynamic which Wendy Chun also elaborates on in her book Updating to Remain the Same. Resolution studies should therefore not just involve a theory about the setting of standard affordances, but also, and maybe more conspicuously so, a studies into the compromised and possibly other implementations of data. In this presentation, I will offer 3 methods to fragment the black-boxed computational image, which is a term I borrow from Alan Warburton, as a means to think through some of these normally unthought or inconsidered compromises and possibilities. An ecology of compression complexities. The choice of an image compression depends on its foreseen mode and place of usage. While the compression of an image that is meant to be printed will probably honor the digital image data to a T, making sure no compression aberrations take place, an image sourced for digital redistribution will likely use an algorithm that will cut away visually less relevant information to enhance faster file transfer. So in short, every image compression renders the image data following a particular bias, benefiting its intended usage while possibly rendering the file imperfect for other modes of use. It is therefore important to realize that bias doesn't just exist in the final rendering of the image. Bias also exists in what technology doesn't show, what is obscured, obfuscated, deleted, or not rendered. So for instance, the lossy JPEG compression, which uses DCT or a macro block compression to quantize space, cutting away useless or under-preferenced data, leaving whole blocks of quantized voids. The lossy JPEG compression has only ever been calibrated to Lena, a Caucasian color reference card, a card that has cast a white shadow on the history of digital images. But what if Lena were black? How would this have changed the JPEG compression? How would this have changed all its subsequent algorithms, including the whole MPEG family? To paraphrase Hito Style, we need to pay attention to the back of the images, or the image data, the spaces that are not captured or processed, where data is missing, or the resolving technology hides something or cuts it away from our view. This is why last year I went to the headquarters of ISO to lay flowers and commemorated the absent, unaccepted and depreciated standards. However, I am also deeply aware that it's not just the International Organization for Standardization that is responsible for these standard shadows, or the embedding of bias and the preclusion of other uses of our media. We actually all are responsible. The developers, independent or not, artists and users. So how do we move beyond or beside these generally imposed flows of data? How can we actually break away from our standard resolutions? I think a starting point is to realize that any resolution is more than just a formal solution. Resolutions involve determinations that can actually be rewritten, they can be fragmented or broken up. And with that understanding in mind, I created a vernacular of file formats. In the vernacular of file formats, also dubbed a guide to databand compression design, I explored the syntaxes of different digital compression algorithms by compressing one image via different compression languages and then subsequently implementing a same or similar error into each file to let the otherwise invisible compression language present itself onto the surface of this original image. But years after the release of the vernacular, these glitches actually became more and more common to popular culture. What once was simply deemed glitch art or erroneous now seemed to obtain a whole new secondary meaning. Like signifying skeuomorphics, these glitches became indexical in their own complexities. For instance, while analog noise would be used to indicate the presence of ghosts in any Hollywood movie, line artifacts usually warn us of the threat of aliens, and I believe this is because in the end humans always win over the aliens, so the rendering of communications of these alternative life forms should not be so complex. Blocky glitches generally signify time traveling, while any combination of these artifacts, possibly mixed with vectors, often illustrate the complexities of artificial intelligence. The statics of glitched compressions has thus become an informed material vernacular. They are what Susan Shupley would describe as material evidence or the material witness of their environment. In an ecology of compression complexities, I mapped these different complexities of compression artifacts. The map features the realms of pixels, lines, blocks, wavelets, and vectors, but on a map, these complexities do not actually exist separate from each other. They do overlap, and this is because while in our computational images these complexities exist only in particular stacks and are therefore somewhat separate, data itself can actually easily be transcoded from one complexity to the next. So while the encoding or decoding of data follows certain protocological or imposed complexities, data itself should actually be considered as a fluid. I can actually listen to a rainbow or take a look at the sound of rolling laughter. In an ecology of compression complexities, I map the different complexities right next and on top of each other, because key to the study of resolutions is the knowledge that data can be fluid. Every string of data is ambiguously promiscuous and has the potential to be manipulated into anything, even into a new complexity. We should therefore actively practice or even train ourselves to maintain a rheology of data. And I use this term rheology here as borrowed from the realms of physics, or to be more precise, from mechanics, in which the term is used to describe the flow of matter, primarily in a liquid state, but also soft solids, or solids that respond in a plastic way. By the rheology of data, I mean a study of how data can be read and displayed in completely different forms, depending on context, software, or interface. But also with regards to our senses, and this is because our senses read and process data in quite different ways. While our ears easily recognize patterns over time, our eyes can specialize at the immediate scanning of a plane for irregularities or clusters. So, different senses can perceive and learn from the same data set in entirely different ways. They give us access to different forms of pattern recognition. One is time-based and the other is space-based. The rheology of data advocates fluidity in our data transactions, but also underlines the possible loss of knowledge that may appear when the formatting of data is treated as a non-fluid, brittle, or predetermined object. As standards stay uncontested, one might end up losing the potential for new or other perspectives. A narrative that was part of DCT siphoning, a work in VR that I made for DMODA, the Digital Museum of Digital Art, and that was later also shown by Transfer Gallery in New York. DCT siphoning is a contemporary translation of the 1884 roman written by Edwin Abbott titled Flatland. But instead of a basic Euclidean object, that is the protagonist in the 1884 version, DCT siphoning features an anthropomorphized DCT, and the DCT algorithm is what lies at the very basis of the JPEG compression. In DCT siphoning, DCT Senior narrates the story of its very first siphon, or a data transfer, together with DCT Junior. Their narrative illustrates their interactions as they translate data from one realm of image compression complexity to the next. Senior tells that when they siphon away from the blocks, which is the realm in which they normally resonate, to the planes of pixels and lines, Junior actually soon gets bored. As they siphon on to the realms that are more complex than they are themselves, Junior actually gets excited and reaches a limit to its stack. As they finally enter the realms of vectors, Junior seems to get scared because of illegibility issues. It refuses the chaos and leaves, but Senior remains in awe. An angel of history calmly sings to its DCTs. This is information. Unlike data, information spans over multiple dimensions. It can move upwards, not just northwards. It finally commits to DCT. I would like to follow this short and quite abstract story with a story from my own childhood, because I think there's a direct connection. I recently found this page of my diary back. It reads, "I finally know what I want to do when I grow up. I want to discover new sounds in space." When the 10-year-old me shared this dream with one of my teachers, I was told that there are no sounds in space, and my dream was shattered. Only later in life I learned that there are actually many ways to listen, and that thinking through sound in space might actually mean to consider an extended form of listening, which can be done through different antennas or by extending the range of messengers one listens to, maybe for instance cosmic rays, different types of particles or waves. That maybe, to a scientist, space could actually be full of sounds. During my Collide at CERN and Barcelona residency, I told a physicist about my re-evaluation or expanded understanding of perception. He responded to me with this story. Every time I watch the stars with my young daughter, I try to tell her, I try to explain that what she is really looking at is the never-ending resonance of the Big Bang. The light of the stars we see today is also the momentary state of resonance of the loudest sound the universe has ever heard. My conclusion is that standard resolutions can be useful determinations. They can work to make our everyday life run smooth. They make things function. But there are also presumptions, which puts them by default at risk to preclude alternatives, to perpetuate harmful kludged ways of running, listening, or understanding, and finally, they can block experiments in new ways or other ways of seeing. Impossible images and the latent image space. During my time at CERN, I interviewed over 40 scientists. I asked them, imagine you could obtain an impossible image of any object or phenomenon that you think is important, with no limits on spatial, temporal, energy, signal-to-noise or cost resolutions. What image would you create? The collection of impossible images I have collected so far is fantastic. They already illustrate a diverse array of limits on resolution or impossibility, but also on the technologies of what imaging can be itself. A preliminary categorization of impossible images would entail images that are impossible due to spatial or time or other types of resolution, images that were deemed impossible in the past but that have become possible today, images that were possible in the past but that are no longer possible, images depending on speculation, disbelief or imagination, and images of objects that can only be inferred involving a substantial signal-to-noise bounty. I organized a collection of impossible images in a low-poly rendition of what I call the unquantifiable blob of impossible images. The blob, or binary large object, is home to the collection of impossible images that altogether illustrate the concept of impossible image and its relationships with affordance, resolutions, and compromises. When you enter the 3D space in front of the blob, the visitor is welcomed by the angel of history. She stands there pointing to the blob, a map reminiscing the realms of compression complexities standing right beside her, while behind her a staircase to nowhere points upwards. One enters the blob through a portal imaging the shadow of dark matter. On the right, an image of the insides of a proton shows 3 quarks, the tiniest known building blocks of the universe. They are smaller than a wavelength of light. In front of us, an image of the quantum vacuum at a slice of Planck constant time is shattering space. Left of it, a missing image, and beside it, an image of a sunset on the Labrador coast from Susan Shupley's film Can the Sun Lie, in which Shupley describes the story of a photographic image that denied to abide the rules of the optical regime. Normally, these images would have never found their way to our eyes, but the hypothetical realms of the blob offer pasture to these impossible renders. They show that thinking through impossibilities means thinking through liminalities. It means to consider and possibly expand the limits of understanding what is possible. The blob gives a shape to the latent image space, the space of any and all images, past and future, which in reality has become a fragmented space of stacked, predetermined actions and affordances, consolidated in resolutions. Standing here, different axes of affordance, titled X, Y, Z and Alpha, cut the blob. They define what is possible to resolve, but also what images are compromised, or in other words, will never be rendered. Through my research into resolutions and the impossible image, I see a need to keep fragmenting the stacks of the computational image. But I also recognize a growing ecology of theories around the liminal image space, including, but not limited to, Virilio's synthetic image, Farocchi's operational images, Rubinstein's fragmented photographic images, Paglen's invisible images, Danson's discorrelated images, Flusser's techno images, Warburton's computational images, and of course Styles' poor image. In a time of exploded and expanded photography, a time that recognizes that photography no longer needs to be representational, lens or light based, these theories help us to understand not only what the image is built of, but also what an image is, or what the latent image space can be. The latent image can be used as a tool to expand our perception, and in doing so, it can open new ways to see.